welcome back to my office hours. In this video, we will discuss the two types of hydrostatic equation, the hydrostatic differential equation, and the hydrostatic algebraic equation. Before we start, it is important for us to define what hydrostatic equilibrium is. Hydrostatics is the study of the pressure in a fluid, or the pressure exerted by a fluid, and is essential to understanding the characteristics of fluids at rest. In hydrostatics, hydrostatic equilibrium is the condition in which there is a balance between external forces like gravitational force and pressure force. As a result, the fluid at equilibrium is at rest. To derive the hydrostatic equations, let's begin with an imaginary cylindrical fluid body. This fluid body has a bottom area of A and a length of L. Its central line forms a random angle theta with the horizontal direction. The elevation difference between the two ends of the fluid body is marked as delta Z. Along the central line direction of this fluid body, there are only three forces. Two forces are caused by hydrostatic pressures P and P plus delta P. The third force is a result of gravity G. The two forces related to hydrostatic pressures can be easily calculated using the hydrostatic pressure P or P plus delta P multiplied by the area A. In this way, we are able to calculate Fp1 and Fp2, respectively. Fp1 equals to pressure P times area A, Fp2 equals to pressure P plus delta P multiplied by the area A. Now let's focus on the force derived from gravity G. The gravity G is calculated as the product of mass m and gravitational acceleration g. The mass m is calculated using the fluid density ρ multiplied by its volume v. For the cylindrical fluid body, the volume v is length L times area A. Lastly, let's not forget that specific weight gamma equals to fluid density ρ times gravitational acceleration g. When we combine all these relationships together, we find that the gravity of the fluid body G is the product of specific weight gamma, length L, and area A. Along the central line coordinate direction, the force related to gravity Fg can be calculated using G multiplied by sine theta. If we substitute the expressions of G and sine theta into the equation of Fg, we will find that Fg is directly linked to the specific weight gamma, area A, and elevation change delta Z. So far, we have found the simplified expressions of Fp1, Fp2, and Fg. Along the central line coordinate direction, let's analyze the three forces acting on the fluid body. Both Fg and Fp2 point at the same direction, while Fp1 point at the opposite direction. Therefore, overall, the forces sum up as Fg plus Fp2 minus Fp1. Now let's assume hydrostatic equilibrium along the central line coordinate direction. At hydrostatic equilibrium, there is a balance between external forces like gravitational force and pressure force. Hence, the summation of all these three forces derives zero. Substituting the previously derived simplified expressions of Fp1, Fp2, and Fg into the summation gives an equation that is independent of the area A and the pressure P. This last equation is only related to specific weight of the fluid gamma, the change in pressure delta P, and the change in elevation delta Z. When we rearrange this equation, we will find that delta P over delta Z equals to negative gamma. When delta Z approaches infinitely small, we then derive the so-called hydrostatic differential equation. The hydrostatic differential equation shows the change in pressure in a fluid at hydrostatic equilibrium are only affected by its specific weight and the change in elevation. If the specific weight of the fluid is constant, then the change in hydrostatic pressure is solely caused by the change in elevation. Because the specific weight of any fluid can only be a positive value, then hydrostatic pressure and the elevation will change in opposite directions. That is, when elevation increases, dz is positive, then dp would be negative, meaning that hydrostatic pressure decreases. When elevation decreases, dz is negative, then dp would be positive, meaning that hydrostatic pressure increases. When elevation remains unchanged, dz is 0, then dp would also be 0, meaning that there won't be any change in pressure in this situation. While hydrostatic differential equation is a simple equation, we have actually made two important assumptions during its derivation. The first assumption is hydrostatic equilibrium. Without this assumption, we won't be able to equate the sum of the pressure and gravity forces to zero. The second assumption is more hidden. When we express the volume of fluid body as the product of its length and bottom area, we have assumed that this volume won't change despite the pressures added on its surface, indicating that this fluid is incompressible. Next, let's integrate the hydrostatic differential equation, with the elevation changing from Z1 to Z2, corresponding to the hydrostatic pressure changing from P1 to P2. In this step, it is critical to emphasize that the specific weight of the fluid gamma must be a constant. The result, after some rearrangement, is what we call hydrostatic algebraic equation. This equation has many real-world applications, especially for hydraulic designs. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.